Hello everyone, I'm Chris, and what I want to do today is demonstrate how we can use Python to simulate a probability experiment and use Python to calculate theoretical probability for the same question. So let me bring in our question and talk a little bit about the example that we are using. And here we have it. And so what we've got here is an example. What is the probability of flipping a coin 10 times, landing on heads 6 times or more? And for the first part of this solution, we're going to look at the experimental solution, which uses random values in a large sample size to calculate the probability. And then we'll look at the theoretical probability, and we will use mathematical formulae to solve the problem. Okay. Now, this is a coin flipping problem, pretty straightforward. First thing we're going to need for our experiments is the random module. Now, to conduct a large number of experiments, we are going to have to define what an individual experiment is, or a test, and so I'll define that as a function. Okay, and for the sake of this function, we want heads to be 1, and tails to be 0. The reason for that is we are counting the number of times that we flip a heads, and therefore giving it a value of 1 makes it easy to count, and it also prevents you from counting tails because they have no value. Okay, when we start our test, the number of heads will be 0. Then we need to perform a certain number of flips of the coin. So we would do for flip in range 10, we're going to do 10 flips. So for each flip, we need to count whether it's a head or not. So number heads plus equals, and here's where we use random. So a flip of a coin can be simulated with a random number between 0 and 1. So we would do the random with the randint method, and then 0 to 1. There we go. So that will count up in 10 flips how many heads we got, and then we're just going to return whether or not the number of heads was greater than or equal to the required score, which was 6. And that constitutes a single test. Flip the coin 10 times, determine whether you scored 6 or higher. And that will tell you whether you passed or failed the test. Now what we want to do is define our experiment. And our experiment is going to tell us the sample size. That will be n. How many times do we perform the test? It's going to be n times. When we start our experiment, we have no successful results. Obviously, we have no tests and therefore no successful results. Now we need to perform n tests. So for now, I don't want to call it test because we're using test as the function name, so we'll just call it t in range n. So that will perform n tests. What we want to do here is add 2 successes when this is successful. Now this returns a Boolean, so all we have to do here is successes plus equals, convert to an integer, run the test, and if the test passes, we get a 1. If the test fails, we get a 0. This will count up how many times we have passed. Then we just want a little information here as we run our experiment. So tell us how many times did we succeed, how many times did we run the test, and lastly, how well did we do? What was our % success rate? And then we can run our experiment. And we're going to start out running our experiment 10 times. In other words, flip a coin 10 times, count up how many heads you got. If it's 6 or more, you are successful. If it's 5, do that 10 times and count the overall probability. All right, so we had 5 successful runs in 10 runs. That's a 50% success rate. Okay, what we can do is just run this a couple of times in quick succession. And you can see it hovering between 2 20, and 50%. 0.2 to 0.5. That's interesting, but 10 is not a very large sample. So let's up that to 100. Let's run that. And you can see we're getting out to the hundredths column here in our probability, in our percentage, 27%, more precise. Let's go a little more. Let's go to 1,000. All right. That's, sorry, you can't see that. Let me bring that one up. All right. There you have it. 38%, 37%, 37, 37, 34, 38. Okay, now can be more accurate, more precise, and more consistent. Let's up it to 10,000. Run again. 38%. Let's up it to 100,000. 100,000 attempts. Good. 38%. Takes a little while to run now. 37.6. 37.6. 37.8. 37.7. Okay. I'm going to run this at 1,000,000. It's not going to take us too long to run it at 1,000,000. So just stand by, maybe 30 seconds. While that's running, we should start to think about the theoretical value. The theoretical value will basically just tell us the total number of successful results possible in all possible results. And that's our theoretical value. Okay, there we go. On 1,000,000 attempts, we got 377,627 successes for a percentage of 37.8% success. Okay, the next thing we need to do here is look at the theoretical. So let's make a function called theoretical. And it's going to be a lot like the experiment, but in this case, we're not going to run a test. We are actually just going to use a mathematical formula. So when we start, we have no successes. Same way we started our experiment. The next thing we do is we count up the total possible successes. So this is going to be, now 6 heads is successful, 7 is successful, 8, 9, or 10, they're all successful. So we want the probability of each of those results added together. So what we will do is say for k in the range 6, 11, that's 6 up through 10, we are going to add the successes that you get that many heads to the total successes so far. So successes plus equals, and now we need to do n choose k, or 10 choose 6, 10 choose 7, so on and so forth. Easy way to do that, import math, go back up to the top, we'll scroll down here, and now we will say successes equals math.factorial 10, that's n, divided by, now it's math.factorial k, multiplied by math.factorial on n minus k, that would be 10 minus k. Okay, once we've completed our loop there, we will know the total successes in all possible flips of the coin. And now we need to know how many possible results are there, no matter what the arrangement of the values is. So we say possible results, and in this case, because there's only 2 values, it's going to be 2 to the 10th power. Okay, possible results equals 2 to the 10th power. And then we just return the success rate, successes divided by possible results. Now what we can do is just print out the theoretical result. Okay, so if we run this, let's lower the number of experiments down. This is going to run 100,000 experiments. We get 37,735 successes, which tells us that the experimental probability is 37.7%. The theoretical calculation tells us it's 37.7% as well. Now that theoretical value will never change because it's a mathematical formula. Let's up this to 1 million experiments, and I'll let that run. And here we should be accurate to about the thousandth place, so to 4 decimal places, which I think is pretty good, but it depends on how accurate you want to be. The more accurate you want to be, the more experiments you have to conduct. Now, this case is sort of an interesting example. There's some variation. We're somewhat off of the actual percentage, but you could run much higher. You could let it run for an hour and get maybe 10 or 100 million experiments, and it should become even closer. Now, in this case, the theoretical probability is not that hard to calculate, but there would be some situations in which you may not know how to calculate the theoretical probability, and so you would use the experimental. You might want to validate your results to see if ballpark is it accurate. And finally, it may just be a way to intuitively understand probability a little bit better. Also, who has time to flip a coin 1,000,000 times? I don't. Thanks for watching, and I hope you tune in again.